Okay, let's see if I can actually do this right. Okay, let's say we have a current loop going this way, and it's going to go around this way. So the current goes around in this circle. And that current loop has an area A. That is what's going to give us a magnetic field. In fact, people think this is the only way to really get a magnetic field. I'm not sure, but that's what they tell me. And so as this is going around, then you're going to create a field. We'll talk about how that is next time. That is going to go up this way, or actually 2 times. So we're not going to generate electric or magnetic fields for a little while. Talk about response in the next lecture. Right? So this creates a magnetic moment M up that way. All right? So what we're saying is this current loop creates a dipole moment. Okay, and how that works is we're going to say the moment is equal to the current times the area. And if you remember from the previous examples, that's basically what the right units anyway, right? We had amps times meters squared was the units of the dipole moment. So we're doing the right thing. It's the right kind of thing. And, we could go into more detail, but we don't like the calculus in this class. So this is how we get our magnetic fields. And when you're doing anything, when you're creating a magnetic field in a lab or something like that, you are either just spinning stuff around in a circle. Usually if you want more field, you just have more turns, right? That's nice. And that creates a higher magnetic field because you've got a greater magnetic moment here. But if you wanted to be really tricky, what you do is you put a paramagnetic material in there, and that amplifies the amount of magnetic field you get. Usually you don't use a regular paramagnetic material, you use a ferromagnetic material, but you use it in a clever way, using properties we haven't talked about, and that's part of the reason why it's clever. And you do that in a clever way, and it actually creates a higher field. So we have M equals IA. The big important thing here is that how do I get the direction? Get it from something called the right-hand rule. So this is the right-hand rule, RHR1. If we're using vector analysis, I can give one sort of definition of the right-hand rule, and it's all easy, but we're not. So we'll have to use the more complicated way, right? It's not that complicated, but it's a different rule for each application. They're all the same rule. It's just that the applications are just different enough that translating from one to the other gets difficult. And basically it says you take your fingers, and you loop them in direction of the current, in the current direction. And then you stick out your thumb that thumb is in the direction of your magnetic moment. Okay, so I take my right hand. This is nice. So it was hard drawing that, but at least I don't have to do the right hand rule with my left hand, right? Because I didn't flip the because I'm not flipping this off. I just have to write and draw opposite. So you take your right hand and you curl it around just like you got here, and you stick out your thumb, and if you're curling in the direction of the current, that thumb always stays in the same direction, which is perpendicular to it and going up. All right? So in this case, that's true. Now, if the current was going in the opposite direction, right, it was going this way instead of that way, then your magnetic moment would be down. Okay, so that's how that works. So let's see, how do we make that work? So you're curling these around. Did it backwards again. Maybe I didn't do it backwards, and that's the problem. So you curl your hand around that way, then your thumb is in the direction of the magnetic moment. So you're curling around with the current, and your thumb is in the direction of the magnetic moment. So this case means instead of the green thumb, you have a red one, right? That's the direction of the magnetic moment. I hope there's no connotations to red thumbs. I've never heard it before, but you never know. Let's see. Last part is this is equivalent to standard dipole. Now, these don't exist in the real world, we said, but we could model this as a charge, not enough room, so don't even try, plus QM at one end of the stick times minus QM at the bottom of the stick. And that gives us a dipole moment, just like we had for electric fields. Now, even though there aren't any actual charges like this, we can't have these charges. We can pretend we have those charges. It'll make some sort of it'll make some calculations easier, like how much force do you have on that thing. With a little bit of calculus, again, with a little bit of vector calculus, again, you know, you don't need this approximation, but if you don't have it, then this is something that's really, really useful. So that says that we have the magnetic moment is equal to Q times D, where, you know, the center to center distance is D, and this Q, I have to remember to write Q sub M because it doesn't have units of charge, because it has units of magnetic charge which don't exist, right? We look for them, but we haven't found them. We'd love them to be there because it makes some of the symmetries of the universe more beautiful. But it's a different sort of thing, and it has a different unit. We'll talk about that unit in the example. We'll also use this again for calculating the force in a non-uniform field next time. And that's actually the reason why this is important, is because this allows you to calculate the force in a non-uniform field, or at least get a good approximation to it, even though you don't have the calculus to figure it out. The simple vector calculus that, you know, somebody might learn as a junior science major. But we'll just skip that and use this approximation. So this and this are equivalent. They'll give you the same fields far away from the dipole. But we'll have to switch between these two ideas to do different kinds of calculations. This is real. This is useful. A useful fiction, but it's useful. Right, so that's the way the world is. Sometimes what's useful isn't. Sometimes what's useful is the opposite of what's real. All right, so tell that to your pragmatist philosophers. Tell that to Charles Peirce with all this crazy "what's useful is real" stuff. All right, I know.